welcome to this explainer. Today we're going to trace a pretty incredible century-long arc. We're bridging a purely theoretical thought experiment, dreamt up at a patent office way back in 1907, to what is arguably one of the most monumental technological achievements in human history. We're taking a journey from the absolute limits of human imagination, all the way to physically measuring the fundamental fabric of reality itself. Okay, let's dive right in by asking you to imagine an everyday scenario that actually completely breaks our classical understanding of physics. Can you feel gravity if you're falling? Now, I know it sounds like a trick question, but the answer to this actually reshaped our entire understanding of the universe. Here's a quick roadmap of what we're going to cover: the happiest thought, the equivalence principle, the field equations, ripples in space-time, and finally, the 2015 historic detection. Let's start with Section 1, the happiest thought. So paint the picture. It's 1907. Albert Einstein had revolutionized physics with his special theory of relativity just 2 years earlier. But he had a glaring problem. That theory only worked if he ignored gravity. He desperately needed a way to unify his new ideas of space and time with gravity itself. And that led to what he famously called the happiest thought of his life. He realized that if a person is freely falling from the roof of a house, they wouldn't feel their own weight. That means, effectively, gravity vanishes in their immediate local surroundings. Think about astronauts on the space station. They look weightless, right? But it's not because there's zero gravity up there. Earth's gravity is actually still exceptionally strong at that altitude. They're weightless because they and the station itself are in a continuous state of free fall around the Earth. During free fall, the local effects of gravity just disappear. Which brings us nicely to part 2, the equivalence principle. That realization we just talked about is the conceptual bridge that allowed Einstein to start linking gravity directly to the geometry of space. To get this, imagine you're locked in a windowless elevator cabin. If you drop a ball and it hits the floor, there's absolutely no physical way for you to distinguish whether your cabin is just resting on Earth, feeling its gravitational pull, or if you're actually in a rocket accelerating through deep, empty space at exactly 9.81 meters per second squared. The downward acceleration of that ball relative to you looks and feels exactly the same. It's kind of a wild concept to wrap your head around, but no physical experiment can tell you whether you're feeling the pull of gravity or just experiencing acceleration. In a local reference frame, they are fundamentally indistinguishable. Gravity isn't just some invisible rope pulling things downward. It's inextricably linked to acceleration and the very fabric we exist in. Moving right along to part 3, the field equations. By 1915, that simple elevator thought experiment evolved into this, the Einstein field equation. You can basically think of this as the source code of the universe. It looks remarkably compact for something describing the entire cosmos, doesn't it? On the left side, you've got the entire geometry of the four-dimensional space-time continuum, and on the right, you have all the energy, momentum, and matter present in that space. This elegant little equation sparked a massive paradigm shift. It showed that matter tells space-time how to curve, and in turn, curved space-time dictates how matter must move. It completely tossed out the old Newtonian idea of gravity as just a simple pulling force. Now for part 4. Ripples in spacetime. Because spacetime is a flexible, stretchable fabric shaped by mass, a pretty profound question comes up. What happens when massively heavy objects move really, really fast? Well, if you take two incredibly compact objects, like a pair of black holes, and have them orbit each other at high speeds, their extreme acceleration disturbs that fabric. They send out ripples. Not light waves, but actual invisible waves that stretch and squeeze reality itself. We call these gravitational waves. And that leads us to our final section, the 2015 historic detection. For literally 100 years, these ripples were purely theoretical. Einstein's math said they had to be there, but the space-time distortions they'd cause were predicted to be so mind-bogglingly small that for decades, scientists legitimately doubted we'd ever be able to build something sensitive enough to detect them. But then, September 14, 2015, at exactly 09:50:45 UTC, the advanced LIGO observatories, two massive facilities thousands of miles apart in Washington State and Louisiana, simultaneously caught a transient signal. Dubbed GW 150914, this blip definitively proved Einstein right, and it captured a truly cataclysmic event that went down over 1 billion years ago. What's so amazing about this slide is how these two spectrograms actually let you see the chirp of the gravitational wave. Notice that bright, sweeping curve going upwards? That's the wave's frequency rising rapidly from 35 to 250 hertz as those black holes spiraled closer and closer together, spinning faster and faster. That exact shape perfectly matches what general relativity predicted for merging black holes. We literally recorded the ringing of spacetime itself. Let's just unpack the sheer violence of this collision for a second. We're talking about two stellar mass black holes here. One was roughly 36 times the mass of our sun, the other 29 times. When they slammed into each other, they formed a single black hole of 62 solar masses. Now, if you're doing the math, you'll notice some missing mass. 36 plus 29 is 65, not 62. 3 entire suns worth of matter just vanished. It was converted entirely into gravitational wave energy in a fraction of a second. For that brief moment, the energy output outshone the entire observable universe. And this all happened well over 1 billion light-years away from us. Right before they hit, they reached an extreme orbital frequency of 75 hertz. That means these two monstrous objects were whipping around each other 75 times a second. They got so impossibly close, they finally just fused into this single, highly disturbed, rapidly spinning black hole. The signal we picked up captured this exact moment, all the way down to the ring-down phase, where the newly formed black hole finally shed its excess energy and settled into a quiet, smooth state. But to truly appreciate the physics and the engineering triumph here, we need to look at the maximum amplitude, the physical strain of that wave by the time it finally washed over Earth. The number is 10 to the power of -21. So what does a strain of 10 to the -21 actually mean in reality? It means measuring a fractional change in distance that is smaller than a single atomic nucleus over a 4-kilometer span. To capture this signal, the LIGO observatories had to detect a change in the length of their 4-kilometer vacuum arms that is so incredibly tiny it defies logic. The engineering required to isolate those detectors from every passing truck, every microearthquake, and every tiny thermal vibration on Earth just to feel this impossibly faint cosmic ripple, it's absolutely staggering. Measuring that incredibly small distortion didn't just validate a century-old thought experiment born in a patent office. It fundamentally gave humanity a brand new sense with which to observe the cosmos. Think about it. For all of human history, we have only been able to look at the universe using light. Now we can physically listen to the fabric of reality itself. Which leaves us with one massive, thrilling question to ponder. Now that we can hear the universe, what else is out there waiting in the dark?